Hey everyone, I'm Praveen and welcome to AI Sparks, where artificial intelligence meets innovation and excitement. On this channel, we spark curiosity and ignite imagination with AI powered insights, tutorials, and explorations. From machine learning to robotics, we'll dive into the future. Today, imagine this: you're standing in a control room, screens everywhere, charts, heat maps, simulations. Outside, in the real world, a city is breathing, cars move, hospitals pulse, factories hum, power grids strain and relax like muscles. Now imagine there's another city, not outside, inside the machines, perfectly synced, always learning, always thinking. That idea is the soul of a paper titled Digital Twin AI: Opportunities and Challenges from Large Language Models to World Models by Rong and Lifang with a large interdisciplinary team behind them. This paper isn't just a survey, it's a map of where digital twins came from and where intelligence itself might be going next. The story starts long before AI hype. Back in the early days, digital twins were simple, almost boring. They were mirrors. You had a physical system, a jet engine, a bridge, a manufacturing line, and you built a digital copy using equations, partial differential equations, numerical solvers, finite elements. Everything was physics first. If the equations were correct, the simulation behaved. If they weren't, everything fell apart. These early twins were powerful but fragile. They didn't adapt. They didn't learn. They didn't forgive bad assumptions. They were calculators, not thinkers. Then reality started getting messy. More sensors, more noise, more data than equations could handle. The world stopped behaving like clean math. And this is where AI quietly entered the picture, not as a replacement, but as a patch. Early machine learning models helped with prediction, fault detection, pattern recognition, but they were still sidekicks. The real shift happened when AI moved from the edges to the core. The authors describe this evolution using a four-stage life cycle. Think of it as the digital twin growing up. From a static child to an autonomous adult. Stage 1: modeling the physical twin. This is where understanding begins. Traditionally, modeling meant writing down physics, Navier-Stokes, heat equations, stress-strain relationships, accurate but painfully slow. And worse, sometimes the physics was incomplete. So the paper introduces a powerful idea: physics informed AI. Instead of choosing between equations or data, you combine them. Neural networks are trained with physical laws baked directly into their loss functions. They are punished for violating conservation laws. They are guided by boundary conditions. They respect reality. This creates models that are faster, more flexible, and surprisingly interpretable. Neural operators take this even further. They don't learn solutions, they learn the rules that generate solutions. Once trained, they simulate entire systems in milliseconds. That's a massive shift. The digital twin stops solving physics step by step and starts remembering how physics behaves. But a model alone isn't a twin, it's just a theory, which leads us to stage 2. Stage 2: mirroring the world. This is where things get alive. Sensors stream data continuously. IoT devices report states, logs capture discrete events, but raw data is chaos. Different clocks, different formats, different meanings. The paper spends serious time here because synchronization is everything. If the digital twin drifts even slightly from reality, it becomes fiction. So the twin learns alignment, time synchronization, unit normalization, semantic consistency. Once aligned, something powerful happens. The digital twin updates itself in real time, not occasionally, not manually, continuously. Now comes generative AI. This is where mirroring stops being passive. Waves compress reality into latent spaces, GANs generate realistic variations. Diffusion models imagine new but plausible states. Neural radiance fields rebuild 3D worlds from images, factories, hospitals, cities, rendered, simulated, explorable. The twin becomes a living simulation, not just a dashboard. But watching the world isn't enough. The real power appears in stage 3. Stage 3: intervening. This is where the digital twin stops asking, what is happening? And starts asking, what should happen next? Predictive models forecast the future. Anomaly detectors find weak signals. Optimization engines suggest actions. Imagine a turbine. The twin notices subtle vibration patterns, not enough to trigger alarms, not enough for humans to notice, but the model knows. It predicts a failure 3 weeks from now. Maintenance is scheduled early, downtime disappears, costs drop. Or consider healthcare. A patient's digital twin tracks vital signs, trends, subtle correlations. It predicts deterioration before symptoms show. That's not monitoring, that's foresight. But the authors are careful here. Prediction without uncertainty is dangerous. So they emphasize probabilistic modeling, data assimilation, uncertainty quantification. The twin doesn't just predict outcomes, it tells you how confident it is. The trust layer is critical. Without it, intervention becomes guesswork. And then we reach the final stage. The most controversial one, stage 4, autonomous management. This is where digital twins cross a line. Large language models enter the system, not as chat interfaces, but as reasoning engines. They read logs, interpret structured data, explain system behavior in natural language. Agentic frameworks let multiple AI components coordinate, plan, adapt, negotiate trade offs. World models imagine futures that never happened. What if traffic patterns change? What if supply chains break? What if weather extremes hit? The digital twin simulates, evaluates, and chooses. Closed loop. Sense. Think, bot, act. Learn. At this point, the digital twin isn't a tool, it's a manager. But the paper refuses to end on hype. Instead, it slows down and asks hard questions. Scalability is brutal. Real systems are massive, messy, distributed. Explainability is non negotiable. If an AI makes decisions about power grids or hospitals, humans must understand why. Trust isn't optional. Ethics aren't abstract. A digital twin that controls reality inherits moral responsibility, bias, data leakage, hallucinated reasoning. These aren't edge cases, they're existential risks. So, what does this paper really say? It reframes digital twins not as software artifacts, not as simulations, but as evolving intelligent systems. Systems that start by modeling, learn to mirror, gain the power to intervene, and may one day manage the world autonomously. And that leads to the final thought. If we can build thinking copies of reality, who is responsible? When the copy makes a decision, the original must live with. That question isn't technical, it's human. And it's a real cliffhanger of digital twin AI. If you found this helpful, hit like, subscribe, and comment which AI system you want to build next. Stay sparked. See you in the next video.